My name is Kareem Khalifa, and today we'll be talking about equivalence and DeMorgan's in predicate logic. Today, we'll look at two topics that we looked at earlier when looking at propositional logic or Boolean logic. Now we'll be looking at it with quantifiers. So first we'll look at equivalence and then we'll look at DeMorgan's. First, let's look at equivalence. Recall that two propositions are equivalent when they're true and false under exactly the same circumstances. Here's one example that we saw earlier with propositional logic. If P then Q is equivalent to if not Q then not P. For example, if I say if Frida is a dog, then Frida is a mammal, that's equivalent to saying if Frida is not a mammal, then Frida is not a dog. However, we quickly notice that this isn't just something that's true of Frida, it's basically true of every dog. Right? So if Cleo is a dog, then Cleo is a mammal, is equivalent to if Cleo is not a mammal, then Cleo is not a dog, and we could keep on doing this ad nauseum. And what we see is that this works universally. That is, all dogs are mammals is logically equivalent to all non-mammals are non-dogs. And if you look at the Venn diagram, it says exactly this, right? If we looked outside of the green circle, we would find no dogs. But of course, this isn't just limited to dogs and mammals. This is a very, very general logical point. Right? You can see that basically whenever you have conditionals nested inside a universally quantified statement, like we have here, you can use contraposition. And it generalizes even further. Right? For any logical equivalence where you have no quantifier, if you tack on the appropriate universal quantifier, you'll have that equivalence preserved as well. You just have to preserve the logical form and map it perfectly, as I've tried to represent here. Nor is that point limited to universal quantifiers. It also applies to existential quantifiers. Right? If there's a logical equivalence where there are no quantifiers, if you just sort of preserve the logical form and tack on some existential quantifiers, you're fine. When we discussed equivalences in propositional or Boolean logic, one of the big equivalences we dealt with were DeMorgan's laws, and I'll give you a refresher on those. What I want to show you is that there's an amped up version of this that we can use once we have quantifiers in our wheelhouse. First, let me remind you of the DeMorgan's laws that we've encountered thus far. We encountered these way back when. That first equivalence states that if it's not the case that both P and Q are true, that's equivalent to either not P or not Q. The second equivalence states that if it's not the case that P or Q is true, in short, if neither P nor Q is true, then both P is false and Q is false. And you remember Cleo had something to say about this. Since it will be useful for understanding how DeMorgan's works with quantifiers, let me also remind you about some basic ways of manipulating the symbols appropriately with just simple Boolean DeMorgan's. Look at this expression. There's essentially three things in it. There's P, there's and there's Q. So when you negate this thing, think of yourself as reversing all three of these things, where the reversal, as it were, of and is or. We see something similar happens with the other DeMorgan's law that we looked at today. In this case, we reverse or and turn it into an and when we push the negation through the expression. Now let's turn to DeMorgan's when it comes to quantified statements. What we see is we basically have two elements in the most simple universal statement. We have the universal quantifier and we have whatever the predicate is, which in this case we're representing with the orange P. We don't have to do anything with the variables. Those are going to stay the same with applications of DeMorgan's. Now, just as before, we have to do reversals of everything. So it turns out that we distribute the negation sign, if you want to think about it that way, right? So the opposite of all ends up being some, right? And then obviously the opposite of P ends up being not P. Here's a concrete example. Let's look at the picture we have here, right? What we could say is not everyone is white. Using our quantified DeMorgan's law, we see that that is equivalent to someone is not white. In this case, the red guy raising his hand up front. So now let's look at the second DeMorgan's law involving a quantifier. Once again, the opposite of an existential quantifier is a universal quantifier, so we flip that. And then the opposite of P is once again going to be not P. And right, so we see that we're distributing yet again. So to choose the example we see in this picture, if we say nobody cares, that says there is not at least one X such that X cares, and that's going to be equivalent to saying everybody doesn't care. That is, for all X, X doesn't care. Okay, so now what I want to do is combine what we've learned about quantified DeMorgan's laws with what we already know about translating the verb to be when we're dealing with quantifiers, right? So let's just go back to this example, but we're going to make it a little bit more complex. Suppose that we say, not all stick figures are white, as is the case in this picture. Okay, let's think about how to translate this. You can actually be pretty literal about this. You see that just as the English sentence starts off with not all, so too does the logical sentence, the sentence in first order logic. And the rest hopefully feels pretty familiar, right? We're basically translating are using the conditional. Okay, so now if we think about quantified DeMorgan's laws, essentially what we're saying when we say not all stick figures are white is it's the same thing as saying some stick figures are not white. And we see that this is exactly what's going on in this picture, right? And so we know how to translate that too, right? There is some X such that X is a stick figure and X is not white. And we see that once again, it's the little red guy up front. Okay, let's look at our second DeMorgan's law with a quantifier. And we're going to once again just vary the example a little bit. Instead of it being nobody cares, we'll make it no cat cares. So to translate this, we already know what to do, right? We've seen this in earlier lectures, right? No cat cares is the same thing as saying there is not an X such that X is a cat and X cares. And in fact, in those earlier lectures, we noted that that's equivalent to the universal statement that we see there, right? That all cats are uncaring is basically what that's saying, and that's what's captured with that universal statement that just popped up on your screen.
Thanks, and I'll see you at the next lesson.